Version control is a system that records changes to a file or set of files over time so that you can recall specific versions later. If you are a graphic or web designer and want to keep every version of an image or layout, which you would most certainly want to, a version control system, VCS, is a very wise thing to use. It allows you to revert selected files back to a previous state, revert the entire project back to a previous state, compare changes over time, see who last modified something that might be causing a problem, who introduced an issue and when, and more. Using a VCS also generally means that if you screw things up or lose files, you can easily recover. In addition, you get all this for very little overhead. So, what is Git in a nutshell? The major difference between Git and any other version control systems is the way Git thinks about its data. Conceptually, most other systems store information as a list of file-based changes. These other systems, CVS, Subversion, and so on, think of the information they store as a set of files and the changes made to each file over time. Git doesn't think of or store its data this way. Instead, Git thinks of its data more like a series of snapshots of a miniature file system. With Git, every time you commit or save the state of your project, Git basically takes a picture of what all your files look like at that moment and stores a reference to that snapshot. To be efficient, if files have not changed, Git doesn't store the file again, just a link to the previous identical file it has already stored. Git thinks about its data more like a stream of snapshots. This is an important distinction between Git and nearly all other version control systems. It makes Git reconsider almost every aspect of version control that most other systems copied from the previous generation. This makes Git more like a mini file system with some incredibly powerful tools built on top of it, rather than simply a version control system. Most operations in Git need only local files and resources to operate. Generally, no information is needed from another computer on your network. Because you have the entire history of the project right there on your local disk, most operations seem almost instantaneous. For example, to browse the history of the project, Git doesn't need to go out to the server to get the history and display it for you. It simply reads it directly from your local database. This means you see the project history almost instantly. If you want to see the changes introduced between the current version of a file and the file a month ago, Git can look up the file a month ago and do a local difference calculation instead of having to either ask a remote server to do it or pull an older version of the file from the remote server to do it locally. This also means that there is very little you can't do if you're offline or off VPN. If you get on an airplane or a train and want to do a little work, you can commit happily until you get to a network connection to upload. In many other systems, doing so is either impossible or painful. Everything in Git is checksummed before it is stored and is then referred to by that checksum. This means it's impossible to change the contents of any file or directory without Git knowing about it. This functionality is built into Git at the lowest levels and is integral to its philosophy. You can't lose information in transit or get file corruption without Git being able to detect it. Git stores everything in its database, not by file name, but by the hash value of its contents. When you do actions in Git, nearly all of them only add data to the Git database. It is hard to get the system to do anything that is not undoable or to make it erase data in any way. As with any version control system, you can lose or mess up changes you haven't committed yet, but after you commit a snapshot into Git, it is very difficult to lose, especially if you regularly push your database to another repository. Git has three main states that your files can reside in: modified, staged, and committed. Modified means that you've changed the file, but have not committed it to your database yet. Stage means that you have marked a modified file in its current version to go into your next commit snapshot. Committed means that the data is safely stored in your local database. This leads us to the three main sections of a Git project: the working tree, the staging area, and the Git directory. The working tree is a single checkout of one version of that project. These files are pulled out of the compressed database in the Git directory and placed on disk for you to use or modify. The staging area is a file generally contained in your Git directory that stores information about what will go into your next commit. Its technical name in Git parlance is the index, but the phrase staging area works just as well. The Git directory is where Git stores the metadata and object database for your project. This is the most important part of Git, and it is what is copied when you clone a repository from another computer. The basic Git workflow goes something like this. You modify files in your working tree. You selectively stage just those changes you want to be part of your next commit, which adds only those changes to the staging area. You do a commit, which takes the files as they are in the staging area and stores that snapshot permanently to your Git directory. If a particular version of a file is in the Git directory, it's considered committed. If it has been modified and was added to the staging area, it is staged. And if it was changed since it was checked out but has not been staged, it is modified. Like most version control systems, Git has the ability to tag certain moments in the history as important. Typically, this functionality is used to tag release notes. To really understand the way Git does branching, we need to take a step back and examine how Git stores its data. As you may remember, Git doesn't store data as a series of change sets or differences, but instead as a series of snapshots. When you make a commit, Git stores a commit object that contains a pointer to the snapshot of the content you staged. This object also contains the author's name and email address, the message that you typed, and pointers to the commit or commits that directly came before this commit, its parent or parents. 0 parents for the initial commit, 1 parent for a normal commit, and multiple parents for a commit that results from a merge of 2 or more branches. To visualize this, let's assume that you have a directory containing 3 files, and you stage them all and commit. Staging the files computes a checksum for each one, stores that version of the file in the Git repository. Git refers to them as blobs, and adds that checksum to the staging area. When you create the commit by running git commit, Git checksums each subdirectory, in this case, just the root project directory, and stores them as a tree object in the Git repository. Git then creates a commit object that has the metadata and a pointer to the root project tree so it can recreate that snapshot when needed. Your Git repository now contains 5 objects, 3 blobs, each representing the contents of one of the 3 files, 1 tree that lists the contents of the directory and specifies which file names are stored as which blobs, and 1 commit with the pointer to that root tree and all the commit metadata. If you make some changes and commit again, the next commit stores a pointer to the commit that came immediately before it. A branch in Git is simply a lightweight movable pointer to one of these commits. The default branch name in Git is master or main. As you start making commits, you're given a master branch that points to the last commit you made. Every time you commit, the master branch pointer moves forward automatically. The master branch in Git is not a special branch. It is exactly like any other branch. The only reason nearly every repository has one is that the git init command creates it by default, and most people don't bother to change it. Nowadays, it is politically correct to call a branch by its default name, main instead of master. But I will continue to use the old term in my materials. What happens when you create a new branch? Well, doing so creates a new pointer for you to move around. Let's say you want to create a new branch called testing. You do this with the git branch command. This creates a new pointer to the same commit you're currently on. How does Git know what branch you're currently on? It keeps a special pointer called head. Note that this is a lot different than the concept of head in other version control systems you may be used to, such as Subversion or CVS. In Git, this is a pointer to the local branch you're currently on. In this case, you're still on master. The git branch command only created a new branch. It didn't switch to that branch. To switch to an existing branch, you run the git checkout command. Let's switch to the new testing branch. This moves head to point to the testing branch. What is the significance of that? Well, let's do another commit. The head branch moves forward when a commit is made. This is interesting because now your testing branch has moved forward. But your master branch still points to the commit you were on when you ran git checkout to switch branches. Let's switch back to the master branch. That command did 2 things. It moved the head pointer back to point to the master branch, and it reverted the files in your working directory back to the snapshot that master points to. This also means the changes you make from this point forward will diverge from an older version of the project. It essentially rewinds the work you've done in your testing branch so you can go in a different direction. It's important to note that when you switch branches in Git, files in your working directory will change. If you switch to an older branch, your working directory will be reverted to look like it did the last time you committed on that branch. If Git cannot do it cleanly, it will not let you switch at all. Let's make a few changes and commit again. Now your project history has diverged. You created and switched to a branch, did some work on it, and then switched back to your main branch and did other work. Both of those changes are isolated in separate branches. You can switch back and forth between the branches and merge them together when you're ready. And you did all that with simple branch, checkout, and commit commands. Let's go through a simple example of branching and merging with a workflow that you might use in the real world. You'll follow these steps. Do some work on a website. Create a branch for a new user story you're working on. Do some work in that branch. At this stage, you'll receive a call that another issue is critical and you need a hotfix. You'll do the following. Switch to your production branch. Create a branch to add the hotfix. After it's tested, merge the hotfix branch and push to production. Switch back to your original user story and continue working. First, let's say you're working on your project and have a couple of commits already on the master branch. You've decided that you're going to work on issue hash 53 in whatever issue tracking system your company uses. To create a new branch and switch to it at the same time, you can run the GIT checkout command with the B switch. You work on your website and do some commits. Doing so moves the IS53 branch forward because you have it checked out. That is, your head is pointing to it. Now you get the call that there is an issue with the website and you need to fix it immediately. With Git, you don't have to deploy your fix along with the ISS53 changes you've made, and you don't have to put a lot of effort into reverting those changes before you can work on applying your fix to what is in production. All you have to do is switch back to your master branch. However, before you do that, note that if your working directory or staging area has uncommitted changes that conflict with the branch you're checking out, Git won't let you switch branches. It's best to have a clean working state when you switch branches. There are ways to get around this, namely stashing and commit amending. For now, let's assume you've committed all your changes so you can switch back to your master branch. At this point, your project working directory is exactly the way it was before you started working on issue hash 53, and you can concentrate on your hotfix. This is an important point to remember. When you switch branches, Git resets your working directory to look like it did the last time you committed on that branch. It adds, removes, and modifies files automatically to make sure your working copy is what the branch looked like on your last commit to it. Next, you have a hotfix to make. Let's create a hotfix branch on which to work until it's completed. You can run your tests, make sure the hotfix is what you want, and finally merge the hotfix branch back into your master branch to deploy to production. You do this with the git merge command. You'll notice the phrase fast forward in that merge. Because the commit C4 pointed to by the branch hotfix you merged in was directly ahead of the commit C2 you're on, Git simply moves the pointer forward. To phrase that another way, when you try to merge one commit with a commit that can be reached by following the first commit's history, Git simplifies things by moving the pointer forward because there is no divergent work to merge together. This is called a fast forward. Your change is now in the snapshot of the commit pointed to by the master branch, and you can deploy the fix. After your super important fix is deployed, you're ready to switch back to the work you were doing before you were interrupted. However, first you'll delete the hotfix branch because you no longer need it. The master branch points at the same place. You can delete it with the D option to get branch. Now you can switch back to your work in progress branch on issue hash 53 and continue working on it. It's worth noting here that the work you did in your hotfix branch is not contained in the files in your IS53 branch. If you need to pull it in, you can merge your master branch into your IS53 branch by running git merge master, or you can wait to integrate those changes until you decide to pull the IS53 branch back into master later. Suppose you've decided that your issue #53 work is complete and ready to be merged into your master branch. In order to do that, you'll merge your is53 branch into master, much like you merged your hotfix branch earlier. All you have to do is check out the branch you wish to merge into and then run the git merge command. This looks a bit different than the hotfix merge you did earlier. In this case, your development history has diverged from some older point, because the commit on the branch you're on isn't a direct ancestor of the branch you're merging in. Git has to do some work. In this case, Git does a simple three-way merge, using the two snapshots pointed to by the branch tips and the common ancestor of the two. Instead of just moving the branch pointer forward, Git creates a new snapshot that results from this three-way merge and automatically creates a new commit that points to it. This is referred to as a merge commit, and is special in that it has more than one parent. Now that you have the basics of branching and merging down, what can or should you do with them? In this section, we'll cover some common workflows that this lightweight branching makes possible, so you can decide if you would like to incorporate them into your own development cycle. Because Git uses a simple three-way merge, merging from one branch into another multiple times over a long period is generally easy to do. This means you can have several branches that are always open and that you use for different stages of your development cycle. You can merge regularly from some of them into others. Many Git developers have a workflow that embraces this approach, such as having only code that is entirely stable in their master branch, possibly only code that has been or will be released. They have another parallel branch named develop or next that they work from or use to test stability. It isn't necessarily always stable, but whenever it gets to a stable state, it can be merged into master. It's used to pull in topic branches, short-lived branches like your earlier is53 branch, when they're ready, to make sure they pass all the tests and don't introduce bugs. It's generally easier to think about them as work silos, where sets of commits graduate to a more stable silo when they're fully tested. You can keep doing this for several levels of stability. Some larger projects also have a proposed, or PU, proposed updates, branch that has integrated branches that may not be ready to go into the next or master branch. The idea is that your branches are at various levels of stability. When they reach a more stable level, they're merged into the branch above them. Again, having multiple long-running branches isn't necessary, but it's often helpful, especially when you're dealing with very large or complex projects. Topic branches, however, are useful in projects of any size. A topic branch is a short-lived branch that you create and use for a single particular feature or related work. This is something you've likely never done with a version control system before, because it's generally too expensive to create and merge branches. But in Git, it's common to create, work on, merge, and delete branches several times a day. You saw this in the last section with the ISS53 and hotfix branches you created. You did a few commits on them and deleted them directly after merging them into your main branch. This technique allows you to context switch quickly and completely. Because your work is separated into silos where all the changes in that branch have to do with that topic, it's easier to see what has happened during code review and such. You can keep the changes there for minutes, days, or months, and merge them in when they're ready, regardless of the order in which they were created or worked on. Consider an example of doing some work on master, branching off for an issue, IS91, working on it for a bit, branching off the second branch to try another way of handling the same thing, IS91v2, going back to your master branch and working there for a while, and then branching off there to do some work that you're not sure is a good idea, dumb idea branch. You can see an approximate result on the screen. Now, let's say you decide you like the second solution to your issue best, IS91v2, and you showed the dumb-idea branch to your coworkers, and it turns out to be genius. You can throw away the original SS91 branch, losing commits C5 and C6, and merge in the other two. Your history then looks like this. It's important to remember when you're doing all this that these branches are completely local. When you're branching and merging, everything is being done only in your Git repository. There is no communication with the server. To dive deeper into the specifics of GIT, I recommend checking out the website that was used to create this video.